Thank you very much for the kind introduction, Thomas. Maybe I can. So I'm excited to be here. Over the, I guess, more than 5.5 of sort of, it depends how you count. 5 years I've been working on verifying DeFi with a fantastic team of people. How many of you know what is DeFi? Okay, some know and some don't. So DeFi, I'll show you, but these are kind of small programs that manipulating, basically defining an economical process, like lending, borrowing. If you are bored in this talk, if you want to hear more about DeFi, you can look into our website. You can also look into a funny website called DeFi Llama, like the animal, and it will show you all kinds of things about DeFi. So basically, these are small code which actually manipulates cryptocurrency. So this is a joint work with many, many fantastic colleagues who are coming from the formal verification community. I mentioned some of them. Satora is actually a large company now, almost 100 people. And basically, we are looking to basically make this formal verification realistic. We believe that our technology is generic, but we are applying it in a very, very specific domain. Thomas says smart contract, but actually this is a special case of smart contract. These are smart contracts which are manipulating DeFi. And they have some unique characteristic. I'll try to explain during this talk. I encourage you more read in our website. These are great people who are helping us actually pushing this technology. And we are also actually learning from people who are outside formal methods, who are more in the area of DeFi and code security. Satora is actually trying to become a major player in the code security, and we are doing well. We are trying actually to basically provide a security solution for people who are relying on the correctness of this code. So what is DeFi? This is a very, very simple slide, and you see here is taking, so one thing that you can see about DeFi, at the moment there is $48 billion in DeFi, and it used to be much more, used to be 200, so quite a lot was lost actually. And it's going up and down, you see, it's crazy. It's going up and down. And this is basically some code, and this code is implementing some kind of economical procedure. For example, you borrow money, you exchange money, maybe you are performing an auction, and this is stored on the blockchain in a smart contract. And this is the idea is that it's actually let you manipulate things without using the bank. So it's a kind of decentralized financial applications. And one thing which is very interesting about decentralized financial applications, there are many things which are interesting about them, but one thing which is interesting, which is actually the motivation for Satora, that many, many bugs happen here, and many bugs here are happening which are causing huge losses of money. So this is one of the most recent one. It's Euler Finance. So this is a fantastic team, actually coming from Europe. And basically what happened, they have done a little change on the code, and this change was exploited, and 200 million were lost. And it is just a very small change in the code, and a lot of money was lost due to this small change. Interestingly, and this is surprising even to me, this money was recovered. Essentially, and that's an interesting story, which is not the topic of this talk. You can find out later. But the idea is actually in the blockchain, you can track some things. And because the code is immutable, actually the money now, almost all of it is recovered. Yen Finance is also a recent one. I think last week, $10 million was lost due to a small, and this is a very, very small code which has been around, a small Solidity code, and there is a small bug, and it was actually exploited. And more of these things are happening. And I want to point out to you that in this domain, a very, very small change in the code, you are changing a very little lines of the code, and it can cause a huge effect in economical effect. And these are basically people who are investing in cryptocurrency and are losing a lot of money because of a small change and a mistake in the code. So this is why we thought that, in fact, it's an interesting domain to apply formal verification. And I think if you want to take from it, why do you want to work on it? And I think there are interesting research challenges, but it's actually the idea is that code is low here. So what happened is that, and usually this is usually in open source, you write this small code, and this code defines the financial process. So and it's usually what it is done, it's immutable. Or at least this is when it's uploaded to the blockchain, the code which manipulates the storage is immutable. So if you have a wrong code, you have a wrong law. So it's almost like hardware in the sense that this is a software that you actually want to make sure it's correct. The code is not always small, and I'll show you an example where the code is large actually, but the idea is that there is some kind of modularity. You can break the code into pieces, and if you are lucky, verify them separately. And another thing which is interesting that here is that bugs are really, really hard. Like the bugs actually can happen, some of them, and I'll show you some of them, they are happening in rare scenarios. And maybe the next thing which actually makes this perhaps the killer application for formal methods is that unlike traditional safety critical software, the idea is here code is changed frequently. So you really need a technology to check. So these companies like Euler, that they change the code, they changed the code, this is a governance code, they changed it because they thought that they have a business advantage in it. So therefore a technology that checks the code in a continuous fashion will be important. So this is the idea, and actually maybe I want to point out, these are the two players. You can see actually Maker is probably number 5 in DeFi Llama if you see, and Lido is number 1 in DeFi Llama. I think they have something like 6 billion at stake. And they are both actually using Satora. They are using formal verification to guarantee their code. In fact, Satora is now protecting about 50% of the assets. And protect means I have to be careful because we haven't many things we haven't formally verified. But we are trying to do our best job to prove the code. So this is something that is not new to this community, but I want to actually point it out. As a community, we are developing a lot of techniques, and I've been here very sort of simplifying. The first technique for checking code is testing and fuzzing, tools like American Fuzzy Lob. But in the area of blockchain, there is Echidna by 12-bit. There is other one, there is Foundry, so this by Paradigm. So these are tools that are doing some kind of random testing. It's of course very useful. There's static analysis that come from this community or from other community. Sound tools like Absinthe, but unsound tools, Coverity, Veracode, Checkmarks, and all of these good, they are very useful. In the area of blockchain, there's Slither. It's an interesting, also a tool by 12-bit. So these are doing sound over approximation. In Satora, we also have some kind of static analysis. The other branch of tools is automatic verification, maybe sometimes called deductive verification. The idea is you reduce the verification to an SMT formula, either CBMC or Dafny or Viper. And there is also proof assistant like Cork, Isabel, K, and others. So these are all very useful techniques. And when we started Satora, we tried to see where we want to go. So this is, of course, the easiest way to go, but we didn't think that we're going to have an advantage there. And also, what we saw from the examples that we seen is that many of the examples that we care about, they have actually behavior which is very, very hard to find with fuzzing, because it's actually behavior that are very, very rare. The other approach is static analysis. That's, of course, very, very useful, but at least in my experience, getting it to work in a domain where you have to prove interesting properties, you're going to have many false positive and false negative. So this is why we didn't take this approach. The third approach, basically bounded model checking or deductive verification, this was the most appealing to us because we thought that maybe it's easier to get the programmer to use it. I'm not saying that the other approaches are not useful. This is what we decided to go, and this will be the subject of the talk. How do you scale deductive verification to this domain? The last approach, of course, very interesting, using tools like Quark, Isabel, people are using it in this domain K, but we didn't think it's where we can use it, and also it's from our experience of other people, it's very, very hard to use on such a complex code to apply interactive term proving. So this is just pictorially showing you what we do. Basically, we are building a tool which is called Satora Prover that you can try, and this tool covers more than testing, and it's incomparable to static analysis that can find sometimes more errors, especially depending on the specification, but also has false alarms. And of course, we are not necessarily finding all the bugs, depending on the specification. So this is just an example. You see this is Sliter. I'm sorry, it's sort of technical. And you see there are many, many red lines. Each one of them describes a potential error in the code. This is a very, very simple code called bang. Do you want to guess how many of them are real? 0. Okay? And this is almost common on these tools. They have many, many errors. Most of them, actually, there's very few. So that's actually, this is not what we want. So what we are trying to do, basically, there are sort of two things. There are these proof assistant. This is very powerful, but very hard to use. And on the other hand, there are all of these very automatic tools. And I pointed out the one in blockchain, but there are others. And Satora is trying to do something in the middle. We are basically trying to do, is it better now? Okay, sorry. You didn't hear me so far? Okay. So Satora is trying to do something in the middle. And basically, we want to build something maybe not as powerful as Coq, but something which will help us prove interesting properties and will be almost as automatic as tools like Sliter. And there are sort of several decisions that we made. I cannot tell you that these are the right ones, but they felt right at this point, and of course we cannot change them. So one decision, and I think I encourage you to build the tools. Satora is doing well economically, and I encourage you to build something competitive. There was already few competitors from our domain. So one decision that we made is that we verify what is executed. So we're actually not verifying the source code, we are verifying the bytecode. This has some bad consequences, but this is our decision. We didn't want to dictate, and we didn't feel we are strong enough to dictate a programming language, and we thought that we understand the semantic of the EVM good enough. This also helped us because we found many bugs in the compiler itself. But this, of course, is hurting us. It's making our tool less scalable. The other thing that we did, and we probably should have done more of it, we started thinking how hard will it be for people to write specifications. And we tried to make the specification as easy as possible to write. And I think we should do more on it, but this was the other thing. The last thing that we did, which I think is a trivial idea, but I don't know why anybody else has tried it, tools like Dafny or Viper, they think that the user can write specifications for procedures. This is not what we want. And nobody can do it. We cannot do it in our code. So we allow the user, it's a trivial idea, we allow the user to write specification only when the SMT fails. And we basically, sometimes we have to use our engineers to help the tool. So the idea is it's a tool which is supposed to be automatic. So what we do, we have the technology for checking the code. At the moment, we actually building also, our technology is proprietary, but we are building open source for checking the spec, something like think of Alloy or things like that. And there is a Satora prover that I will talk to you about it. And there are also tools to check the spec. For example, Gambit is something I'll show you. It's a tool which is developed by Chandra Nandi. The idea is you mutate the code in order to check the spec. Because what we are finding out from our customers, they make many bugs in the code, they make equally number of bugs in the spec, okay, if not more. So getting the spec right is very hard, and we are doing many other things to check the spec. We are also thinking of monitoring, and this is something that's also in Chandra's code, and Chandra's group, and we are working on it. So this is, of course, not new in this community. How is it working? There are invariant and there's a code, and there's either proof that it's correct and or counterexample. It's again like Dafny or CBMC, but it's a bit different because we are not writing the specification in the same file. We are writing the specification in an exogenous way because, in fact, the specifications are written in CVL and the code is in EVM. Okay, so the idea is we do not, and we want to make the specification reusable between different versions of the code and sometimes between different pieces of the code. And we understand that writing the specification is way harder than writing the code. And of course, because we are relying on SMT, occasionally the tools fail. There are timeout of the prover. I'll tell you a little bit about what we are doing, and there are much more to do. Okay. So this is deployed, and it's deployed sometimes as part of the CI, as part of the build of the customer. You see that here, basically, every time you have a new version, assuming that your environment do not change, you rerun the code. And it's basically integrated into your code, like exactly to prevent the bugs like you have seen in the Euler case. Inside, it's fairly more complicated. I won't be able to explain you everything, but you see it's actually, there is a big tool chain. It runs from the Solidity to the EVM. Of course, that's not our development. And then there's the spec, which we compile to our intermediate representation. Think of a tree others code and others. Then we do actually abstract interpretation to simplify the three others code. And then we generate verification condition, tools like Boogie or Dafny. We generate the formula, and then either find a bug or have a proof. So in the abstract interpretation, we do actually things which are natural, but basically we are making certain assumptions about the EVM code. We are not actually verifying arbitrary EVM code. But these assumptions are being checked. So this is actually the idea. We call it trust but verify. It's standard in our community. And then we apply abstract interpretation of low-level code, basically memory analysis, points to analysis. We recover the types and the control flow information, and we use it to check these things. And you see here, that's one example of a bug in the Solidity compiler, which was identified by the tool. The idea is, in fact, we use this trust by verify, and we found out that one of the assumptions that we have on the code are broken by the tool, and we report to the compiler team, and they fix it. The other thing that we are doing, which is still we have to do many, many things. We have many experts in the team. We are actually making the SMT works better. We're also collaborating with the Z3 and the CVC5 teams to build actually sort of specialized SMT solvers for these domains. So this is a very, very common example. This is a very, very simple DeFi. You see you transfer money from one to another. And the invariant here is that the sum of the balance is still a constant, is equal to the total. And you see it is broken because actually when you do self-transfer, you're actually breaking the code. So this is a very simple example that is caught by our tool. It can be caught by other methods. It's a very simple example. And basically what happened is that when you change the code, you see when you make the code actually simpler, this invariant holds, and the tool can show that the invariant is preserved. Basically, if the invariant holds before the code and you execute the code, it's preserved. How does this fit? And that's actually maybe something that's potentially interesting to this community. We have been working in formal verification for a long time. But basically, the question is, where does formal verification sit in the software engineer lifecycle? And I can tell you that DeFi is an interesting domain in the sense because you have this small code which is carrying a lot of money. It's almost like a safety critical in the sense that people are willing to invest a lot of money in making the code correct. And one thing that they are doing this procedure which is called manual auditing. They will basically approach somebody to check the code. This is a very, very useful thing, okay? It's a very, very useful to have somebody look into your code. And the first thing that people told us, and actually that's where our competitors say that we replace auditing. This is nonsense. We cannot replace auditing. It's not the case that we can replace the human in the loop here. we are making the human better. That's at least my feeling from day one. So you see, this is how it goes. You'll take the DAP, you get the specification, you do the formal verification, but after it, a human has to look at it. Maybe it's a Satora engineer, maybe it's a community, but somebody has to look at it, because at the end, and again, I know everything is saying about machine learning, but at the end, the human has to check that everything is correct, and this is at least my belief. So basically, we have all this technology, but at the end, there is a human that is looking into the code and looking for things which are missing. So maybe this is the thing that you can see. I think it's a huge success for SMT Solver for our domain, is how many bugs we are preventing and how many bugs we are finding. So these are few projects that we work. Aave, Compound, Balancer, these are DeFi that are carrying significant amount of money. You see here the value, I think it's changed a bit. And these are teams which are very, very good in software insecurity. So they work with the best auditing team. And basically what happened, they engage with us after they work with all of these fantastic teams. And the idea is the SMT Solver is able to find bugs after these auditing. I think it's a good practice to find it before, basically before auditing, but it's also nice that we can prevent these bugs just before the code was deployed. Okay, so now I'm, I think, halfway to my talk. I want to start being a bit more technical, and please sort of try to explain what actually have I learned here. And this is something I try to prepare for this talk. And some of it is perhaps will not be new to you, but a lot was new to me. So these are kind of 5 things at least that I learned. And first one, I'm sure everybody knows, but I want to stress it again and again. The hardest problem in formal verification by far is writing specification, okay? And this is actually where Satora makes small progress, and I think way more progress is needed. How do you actually formally define? And this is actually a narrow domain. There's financial process. It seems like there is a chance for people there being temporal logic, finding the way to write specification. The interesting thing that we found, which was very surprising, and it's counter to what people found in the hardware, that a lot of good people are willing to write specification in DeFi. And they are doing a good job. I can show you some of the things, but they are doing a good job. So these are people without formal verification background, but they are doing a good job in writing formal specification. And another thing that we are finding, and we are making baby step here, is that sometimes generic specification get you somewhere. So basically you write specification which is good for all DeFi. The other thing that we find, and that's because we are working in low-level code, that there is a huge technology aspect. How do you bridge the gap between the high-level spec and the low-level code? And this is where technology is developed. We have some things, but I think many has to develop. The third thing is probably what's very interesting, especially for a tool perspective, if you are building tools like Dafny or Viper or other, actually getting the tool not to time out is one thing, but understanding the result is another thing. It's very, very hard for us and for our people to understand the output of our tool. And our tool is useful for finding bugs and finding proofs. But in both cases, it's hard to understand this. When we are finding bug, it's hard to understand. And when we are not finding bug, it's hard to understand why we didn't find a bug. Okay? And I challenge you, if you think that it's different from Dafny, go ahead. The other thing that is surprising, especially for people, that despite the fact that this is such a small code, it has all the nightmares that you can think of. And our code has everything here. I pointed out nonlinear, there's intercontract, memory, storage, linked list, everything is here. Indirect calls, dynamic loading. I'm talking about here the Ethereum virtual machine. I know there are cases that it's slightly simpler, but still is the case. And the last thing, of course, is SMT is an undecidable problem, which means that a lot of things has to do in the SMT solvers. And we are doing many, many things, but more can be done. And it's surprisingly unstable in the sense that you can change a formula slightly, even reorder the variables, and it goes from timeout to infinite, to 1 second. It's surprisingly how fragile this technology is. And I can show you what we are doing here. Okay. So I start with my favorite one, is basically how do you write specification here? And I'm not expert. I have tried, and I encourage you to learn more. So let's think of solvency. Solvency is a very natural concept. It's going in banks, it's going in everywhere. The idea is that you cannot run to the bank and take all the money, okay? And basically, if you think in temporal logic, you basically say that no matter what, if I am depositing my money, okay, I should have eventually, or in some situation, maybe with CTL or whatever, I'll have a situation I can be able to withdraw it. So you can define it in some kind of a temporal logic. Unfortunately, I do not know how to reason about these formulas, okay? And this is, okay, good. I tried to formulate it here in temporal logic for every owner, for every asset, for every reachable state in which it was not yet withdrawn or transferred. There exists some scenario under which the owner can withdraw the money. And in fact, this is interesting because most of the bugs that Satora found are problem of solvency. And most of the cases that people actually, so this is interesting. Maybe you want to build a tool like this. This is not what Satora is doing, but maybe you want to build it. So what is Satora doing? We write specifications for things which are, I don't want to say, they are kind of weaker. We check other properties of the code and we check safety properties. We only check safety at the moment. And these are kind of safety properties. For example, the system has sufficient balance to pay. The system has already more than its debt, for example. And under certain condition, maybe the owner can withdraw. You can check the code and see that there is a precondition under which the owner can withdraw. And we use it with the SMT solver. If the SMT solver finds a behavior that violates that, that's great. The customer loves it. If this is proved, it means that we think it's correct, okay? And this is what we are doing. We are writing these specifications. We are not proving solvency. So this is what we do. So the beautiful thing about these kind of things that they sometimes work. This is a very interesting use case. So I told you that basically people write specification. So this is a specification was written by this guy called Barry from MakerDAO. So he's basically a developer, engineer, but I think he has background. So basically what he did, he took an invariant of the code, so that's Maker. Maker, they are doing basically a stable coin. It's a coin which is supposed to be one-to-one with the dollar, okay? And what he wrote the invariant that the code is stable, okay? And basically, he tried to check with the tool. Actually, he thought that he verified it on paper. And this is what happened. The tool actually found a violation. And this violation is real, actually. It tells you that the init function can actually violate the invariant. You see, the invariant here is the sum of the debts. It's basically that you have enough money to cover your loan. And this was actually found by the system. The SMT solver was able to find this violation. And it's actually a real violation. It's not so difficult to fix. It's basically what will happen. You make sure that in the init phase, you actually cannot allow this behavior. So this is exactly the example that we have, and we got it by writing a specification of the behavior. This is even nicer. This is a sushi swap. So that's basically what is called constant pool. Constant pool is that you have two tokens, and the multiplication is constant. Okay? So this is an economical procedure. And there is this function called burn single. It's an operation that allows you to burn one token. And the tool actually found a bug. And this bug is a bug which is very interesting. It's a bug that allows you to deplete the money. You can take all the money. In this case, I think it was at this point $4 billion. And it will allow you to take, the attacker can take all the money. And how is it found? It was found using invariant. In this case, the invariant is very simple. You have this token A and token B, and you make sure that if one of them is greater than 0, if and only if the other one is greater than 0. And you see here L and Benz are holding. And you see that now the A has 400 token and B has 0 token. So the invariant is broken. And what is the consequence of it? So remember, Satora is like tools like Dafny or Viper. It just checks induction. It's basically start from a state which is satisfying the invariant into a state which is violating the invariant. But what I'm showing you is something that was not produced by the Satora prover. It's something that we produce manually. So here you see a trace which actually violates that. First Alice deposit, then Bob deposit, then Alice transfer. So then there is this swap, and in fact all the money is gone. So it's basically showing you how you can actually deplete the money by breaking the invariant. And again, this Band-Siegel operation, this is what Satora is doing, is checking this inductiveness of these properties. So that's it. You see that you take the state from the invariant, and you go from there is a transition from a state that satisfies the invariant into a state which violates the invariant. Okay, so the second thing I want to talk about is how do we reason about the low-level code. This is where we are doing things which are standard in this community. We are using Ghost. We are basically allow you to define Ghost variables, and we translate them into the low-level code. So here you see ERC20. This is code. And then you see that here is a linked list. It's the same thing. You see that now you have a linked list on the code. There's basically showing you all the property that you want. And actually you see there are some bugs here. And you see that the tool is able to find the bugs. I'll show you in a second how. You see that you violate the induction step, and you also violate the induction step. And the property that we are showing here is here hard to see. But basically, we are proving a quantified property for all ID that if the value is not 0, then the next is called to the ID. And we also show that the prev and next, they are complement to each other. So again, this is quantified invariant, and we can check all of it in the low-level code. So here you see the code with the invariant. So you see that the property about the next and the prev. And you see that, in fact, we write now a quantified invariant that for all the address, the next and the prev, they are complementary. We can also reason, if you know about reachability and transitive closure. In fact, it's supported, so we can actually write it in the code. And then you see that it's able to prove the properties about the quantification. It's able to prove you all the properties about the low-level code. And maybe interesting thing, this is of course not complete because we have quantifiers. It is complete for EPR, and we have actually cases it's EPR, but we are able to prove it. Okay, so now actually this is sort of, I think, the most interesting, at least for me, is sort of how do you understand the output of the prover? Because I show you all these bugs and it looks nice, but how do you understand the output of the prover? So what happened when the prover found a counterexample to induction? I show you this example that I told you that we prevented this bug of depleting the code. This looks nice, but you know how long it took for us from the time the prover found the counterexample until we understand it's real? It took us more than 2 weeks. And it was very hard for us to trust our tool to understand the result. And even though it's not anything to do with the SMT, it has to do with the complexity of this code and how to reason about it. Okay, and I try to explain here. We have actually a nice user interface in the Satora prover. You can show the trace, you can show all these things, but it's fairly complicated to reason about these things, even for good engineers. And the more interesting the bug, the harder it is for us to understand the output of it. Okay? And this is a very nice bug, but you see, it shows you the list of values. It shows you what is violated. you can go and you see actually the assertion is violated. That's easy. You see now there is this if and only if which is violated. And you can see it becomes 0. So you have to do some kind of a backward slice. You have to go back on the code. And then you see that it's burning. And you understand what is going on. So you understand the change. And then how can you get reserve? So you have to somehow go reasoning backward, forward. You have to somehow understand the code, what went wrong. And the last one you see actually basically this is what happened. You see actually the properties of the input state which is violated, but you also see that there is something wrong in the code which is being changed. So this is very, very tricky for us to understand the output of the prover. And of course, we are doing a lot of things. We are calling the SMT many times, but it's not just the issue of the SMT, it's understanding the results here. Okay. So maybe the thing which is even more interesting, what happened when the tool proves the property? Okay? It looks like great. Of course, we can generate a proof with the SMT, but Satora is not doing it. Because we know that it's not just the SMT problem. We are doing a lot of software. We have complex code which is not checked. The Satora prover is a very, very complex piece of software. So I'll give you an example. This is really nice. It's a fantastic team, US-based, called Notional. They are our client. They wrote their own invariant, very, very good team. And they did auditing, they did everything. And here in this domain, on top of auditing, there's a lovely idea of called a bug bounty. They are white hat. So these are people who you pay them money. They are finding bugs before the hackers do it. For example, there is this company called Immunify that are doing this bug bounty. So you see, these guys, after they launch with auditing and formal verification, somebody got $1 million bug bounty. Okay? So that's not so good for us. Okay? That's not so good for us. Interestingly, the customer actually changed with our tool. The customer checked exactly the property that the bug bounty is supposed to do. Okay? So look at it. Basically, what is the property? I apologize, it's a bit too low level because we're talking about solidity. But the idea is you see that asset cannot be both bitmap and active. The idea is actually the invariant is trying to prevent double spend. This is the worst thing that can do, that you can use your money twice. And the invariant is checking it. And when they told us about it, we were not very happy. So that's not what you want to hear, especially this, we live in Israel, they live in the US, it comes in. So that's not what we want to hear, this kind of bugs. And we need to understand what happened. Is it a bug on the SMT, static analysis? We have many, many things that can go wrong. So what did go wrong? Anybody wants to guess? We didn't know, but anybody wants to guess?
Operator precedence?
No, the invariant is wrong. That's what happened here. The invariant is wrong. What do you mean by invariant is wrong? It's actually tautology. Okay? It's almost the right invariant, but it's tautology. So let's try to understand what happened here. So this is the invariant. First of all, it checks that I is between 0 and 9 because they are trying to prevent overflow. This is not relevant. We should ignore it. The interesting thing, you see the invariant has conjunction and disjunction. And logic is confusing. I apologize. I mean, I've been working on logic, but it's very confusing. I agree. But the idea here is there is implication, and the tool is checking implication. Okay? So basically what you see, if getMap account is not 0, then you have hasCurrent map account is 0, and getMap account is not 0. So basically, this implication is just hold vacancy. Okay? And the next one, it's a bit harder to see. But the idea, you see this, if getMap is not equal to 0, getActive mask is account is not 0, you don't understand. But in the code, this is actually bit vectors, and there's a subset of bits here. Okay? So basically, this is actually the case that tautology invariant is written. And when we see that, when we saw that, we realized that we were stupid because we should have, before we even started the tool, we should have checked vacuity. And we are doing it at the moment. At least we are preventing this kind of situation. So we are checking the invariant. The problem is not a bug in the code. There is a bug in the environment, and it's good to find a bug in the environment, and actually it's easier for the SMT to find a bug in the environment. So we could have prevented, we could have saved this $1 million by checking the environment, and in fact we are doing it. So that's what we do. Okay, the interesting thing, by the way, that the environment is almost right, actually. The real environment is a bit simpler, and in fact, it checks the code. It checks the bug, and it finds the bug. It's very interesting, and actually, when they change the code, we use the right environment, and we prevented another error. So if you have, environments are great. If you can get them right, that's good, okay? But they can be scary. They can be scary, but that's the idea. You see, the real environment, actually, I have here a link. I'm not going to be able to show you, but you can use it in our tool. Basically, there was a clause which is supplementary. You see, with the real environment, it actually is able to check the code, and we could have saved this $1 million. Okay. The other thing that we are doing, which is very, very recent, it's been very useful, and I think there's another group in Waterloo is doing it, but I think it's very useful in this community. The testing community really believes in mutation testing. And in formal method, sort of, at least I wasn't doing it. But the idea now, Satora prover, we have open source tool that mutate the code and try to check it. And the idea is if you didn't, sort of, in this case, we would cut this example. So the idea is we mutate the code when it's verified, we mutate the code and try to see which rules are verified. So here you see, for each rules, you can see how many mutants are caught, okay? And you see here there is these rules that are caughting mutants, okay? There's also the notion of solo rule. A rule is basically that only it actually sort of, no mutant are caught. You see one of them is a solo rule. It's actually similar to the idea of solo bug. If you are familiar, are you familiar with this idea of solo bug? The idea is if you have a bug bounty, and if you are the one, for example, Code Arena, if you are the one who are the only one who providing the bug, you get more money. So these are the things that we are doing, and this is done by Chandra in his group, and actually we have an open source tool that are checking the spec. And you see that we are checking the mutants, we are mutating the code, we have an automatic source to source that modifies the solidity, also Viper, and then we can check that if it's violated the spec, and if there are not enough coverage, we add more rules. So that's the idea, is sort of trying to check that the spec covers enough. The last thing that we do to check the spec, which is very, very useful, is actually using Unset Core. The idea is Unset Core allows us to do generalization. So basically, when the formula is unsat, we're trying to understand why reason it's unsat. If you are working on source, it's easy for us because we're working on the bytecode. It's slightly more complex because we have to go back to the source code. So here is an example. You have this spec. You see you have a tautology. This is also something that we have. You have a parametric rule here. You see you are calling a function that you don't know what it is. We are checking a property. That's very useful specification, so some kind of high-level specification. On the right-hand side, you see the tag. This is generated by our tool. It's 3 others code. And now we're getting this tag. You see that all the code is translated to the 3 others code. And now you see there is an SMT formula. This is the formula that we feed to the SMT solver. And it feeds to the SMT solver. It tells you that it's unsat, so all this formula is unsat. And actually, you see the unsat core, so the unsat core doesn't include everything. And you have to see what's going on here, but it's, you can see here that basically what happened is that all the function, it's not actually used here. So that's basically, you see that something is wrong. In fact, you are calling a function, but in the verification, actually the function is not used. And this is where the human understands that there is a problem. So it's a tool that actually can check vacuity using the SMT solver. So maybe the last thing I want to talk about, and maybe I should have had all the talk about it, is this is the technology. How do we deal with the SMT complexity? The answer is that we are spending a lot of effort, but we need much more, and we need help. We need to reason about all these things. It's complicated for us. And I'll show you some of the things that we are doing, but we are looking for more. So the first thing that we do, it's a very, very simple technique, surprisingly useful. Basically, we split. Remember, when you're doing formal verification, whether you're doing bounded model checking or deductive verification, it's the same. You always have basically a program without loop. Because if you have a loop, you are starting from invariant to the invariant. So the idea is you have a loop-free program, and you're trying to verify it. Here you see a simple program. And you run it to the SMT solver, and the SMT solver times out. Okay? So what do? We can use procedures or something, but this is our last resort. There are automatic tools that we are doing, and the simplest one is splitting. We basically build a control flow graph, do some kind of domination, and we split. So you see here, we split the program into two programs, and then the first one is unsat. It means there's no bug here. But we don't know yet that there might be bug in the second program. So we try the second program. It's also timeout. So we recursively try to check this other subprogram and so on. And the idea is we call the SMT solver multiple times and basically try to see, hopefully, either we time out on everything or we unsat on everything. It's a very, very simple heuristic. And I remember sort of talking to the SMT solver, gurus, they told us this will never work. So let's see how well it works. So the answer is it works well in some cases. So you see that in the vast majority of the cases, it's drastically improved runtime. It does create 3 new timeouts, but it solves many of them. About 60, it solved them. It's of course, like many other things, it's option, but most of the cases we use this option. We use this option, and we basically split it and give a smaller problem to the SMT. The other thing that we do, and maybe we can do better, but in our program, there's a lot of nonlinear arithmetic. It's very, very essential to DeFi. The financial application has a lot of nonlinear. And we don't know what to do. We are investing many, many things. But one thing that we do, we have our own encoding that we're supposed to help, and they do help in certain cases. So we basically do over-approximation by uninterpreted function. You see here, for example, for nonlinear, you have a multiplication. So we basically make it uninterpreted, and we write some natural axioms. You see, like multiplication by 0 is 0, commutativity, and others. So this is, of course, sound and not complete. It means that the SMT solver can give you a bogus counter example, but then we can call the real nonlinear when it does. We don't actually have to show it to the user. Another thing that we do, and this is common, and I think people are doing it, but we are doing it in an automatic way, we throw into the solver hints. Basically, we give the solver some formulas which we know they are correct. SMT also knows what's correct, but sometimes it takes SMT a long time to find it. And we just go this. So, for example, here is about domain-specific about overflow. You see here for every condition in the program, we generate this formula that actually gives you the correlation. We are working on a 256-bit integer, so it gives you this correlation. And we give these formulas to the SMT solver, and this helps. So here, this is actually a huge game changer. It's a huge game changer. We are still trying to understand, but it's the case that many cases, actually, this is actually giving us a huge, you see here, that is making things way faster when we are doing this over-approximation. One guess is that the properties that we have are not sort of related to the nonlinear, but we see a lot of things. There is still one new timeout, but in general, it helps. The last thing that we are doing, and this is only baby step, we are investing a lot in individual SMT solver, and we are using them all. We're actually starting to use them in parallel. We are also combining SMT solver, which seems to be a good idea for us. So basically, the idea, we have this idea of learned clauses. SMT solver, when they fail, they actually produce learned clause. CVC5 used to produce it. Now we ask Z3 and Nikolai is produce it for us. So the idea is we can find these learned clauses, and then we can feed them even when they do nonlinear. So we actually can combine SMT solver on different subsets of formulas and when they succeed. So we are not actually using just one solver. We are combining multiple solvers in addition to the splitting and all the other things. What do we do for quantifiers? I mentioned EPR, but in fact, we usually are doing the grounding ourselves. We basically have a heuristic to do grounding, which are sound and not complete. We have an initial experience that it's doing OK, but we need to do more. Maybe this is the last technical, but it's actually most of our code, and this is where most of our technology is. We want to use the SMT solver only as a last resort. So we are doing a lot of things at the abstract interpretation to simplify the SMT. In particular, we reason about memory. We reason about basically we avoid array axioms, which are making the SMT work much worse. So here you see initial data. Basically, we try to use without the static analysis. You see that actually it's run much slower, has many more false positives because we have to use Havoc. And if we do the splitting and we do the static analysis, it's way better. This is actually something that we should probably write as an article because we have done a lot of things here in the abstract interpretation to make this abstract interpretation work. I think I'm running out of time. So I want to get you just a few takeaways. We are still working on it. It's very far from being working. But I want to actually give you some things that we learned. So I think I already mentioned formal verification is useful for DeFi. There's a lot of money at stake. I think it's really a beautiful idea to basically apply techniques here. The code is tricky. There are bugs that are hard to find other ways. But more is needed, and I mentioned already the specification, static analysis, SMT. Some people are thinking about programming language design. It's fine. And we took a very, very small step, and we basically look at it based on the code of our clients. I want to actually point to you also the takeaway from Yaroslav, who is leading the SMT team. So basically, there are actually surprising things at the SMT level. Actually, that LIA is sometimes good enough for nonlinear, and I think it's surprising to us, but it's not always the case. We believe because our specs sometimes do not involve the nonlinear. Unset Core is really, really useful. I already mentioned to check the spec. Array theory and bit vectors, these are the things that we need, but it's very complicated, makes our life complicated. This is where static analysis is useful. And one thing, this is unfortunate for us, but I want to tell you the truth. When we write interesting spec here, it times out. We have to do something. Usually we do something, either we write procedure, and actually some users, they already know. So they will take the complex code and already start writing spec on it. Memory analysis is key, I already mentioned. This is something I want to close. Again, it's something that probably you have seen, but I want to actually tell you formal verification. Of course, we think it's for proving bugs, but from the model checking community, we know it's actually the biggest value is finding bugs. Hardest problem is computational. I think I already mentioned the specification. The formal verification doesn't produce a bulletproof code. We have seen it with the notional and other. There are a lot of things you want to check. Some of them, price manipulation, other things. But we do think it's drastically improved quality. We see that actually clients that use us, the customer actually knows that we are not able to verify everything, but the part that we verify, they steal more from each other because they see it's more safe. So it actually is increasing safety. It's not replacing auditing. I say it improves auditing. And hopefully, many of our clients, they encourage us too late, and we want them to encourage us too early, but it's hard for us to convince them. The conclusion, bug finding is hard, auditing is just one thing. Static analysis work in SMT together. So this is a case, I think, that abstract interpretation and static analysis are better than each of one, because static analysis, abstract interpretation here does not have false alarm because we have the SMT. And also abstract interpretation really helps in the complexity. And we have this automatic formal verification. So thank you very much.
Mooly, we have time for questions. Mooly, great talk. It occurs to me that finance is actually a perfect example for multi-agent reasoning. Like your solvency property really shows CTL is not enough. You don't want one path on which you get your money back. You want, no matter what all the other agents in the system do, you have a strategy to get the money back. Any thoughts on that?
Yes, so that's a great question. So the question of Tom, that it's basically a perfect example of multi-agent, and it's actually going, so I think you're right, but I think what happened to us, and this is Satora, it's not academic, we come to the customer and we tell them, I think there are actually researchers who are doing it and probably doing a good job, but when we come to the customer, in the customer there's so many low-level stuff. And the question is, and we think maybe your idea is good for writing a language to reason about design. So maybe you can do this and then later on go to the code. At the moment, we are really starting at the low level, but you're absolutely right that it seems like a perfect example for multi-agent. And please, if somebody can reason about design, and maybe you can see later that it's preserved by the code. The code that we understand, maybe I haven't told you, but one of the things that's surprising to us, and maybe you won't believe, many of our customers, they are heavily using of assembly code. So that's very, very complex, and that makes our tool like very, very hard for us to use.
More questions?
Yeah, so one of the main domains where formal verification was first used was in the aerospace industry, where there was a lot of regulation because of FAA, right? Is there, because of the recent fraud, right? There's a lot of news about fraud and crypto, right? We've heard a lot of that. Is there any space for formal verification to do something about fraud prevention and make these things much more resistant to fraud?
Yes, so I'm not an expert. I believe probably the answer is yes. We have seen a lot of things. You're totally right that in avionics software and safety critical, people came with regulation. Here there's no regulation. Web3 is far behind Web2, even in deployment. And it's a weird domain. I mean, one of the things that we are a small company and our influence is very limited. And our customers have their views and we are trying to serve them. So it's an interesting question. I think it's combined both technology. What can the technology prove? Can we prove fraud? Can we prevent fraud? And there are probably other experts, and also how people will react to that. We are seeing that in the crypto, people are really against regulation. And on the other hand, there are people who are trying to enforce regulation. I've been in this last year, I think or last few years, I've traveled more than I've traveled in all my life. And one of everybody that I come to, I see somebody say, can Satora enforce regulation? And I don't think we are in a position to, I don't, at least myself, I don't. So we are just, but it's a great question. If we can prevent fraud with formal methods, or can do something that makes it useful.
So my question is, so there is this notion of explainability in the machine learning domain, but there is not much, at least to what I know. Is there the similar kind of studies for how good or how simple a specification is? So there are a lot of specification languages, temporal logics and modal logics and blah blah. And is there a systematic study of these specifications, whether the simplicity of the specifications is it comparable, something like that? And if not, is there a value to such kind of formal study of or formal analysis of the simplicity of specification in this domain?
So the answer, I think, in the model checking, there have been some study that shows that many of the specs that the engineer write are vacuous. In our area, in the DeFi, I'm not familiar with it. It's a small domain and it's a young domain, and Satora doesn't have many clients at the moment. It's hard for us to, but definitely there is a place for it. I know actually people say that they are using Satora with ChatGPT. Don't ask me how and whatever. So there is a space for that. There's a space for learning spec. There's a space for checking the quality of the spec in some quantitative way. Definitely, we are just basically really heads down with our tool, fixing bugs, dealing with mundane issues. But yeah, it's definitely interesting if somebody can check the spec. People are writing spec now. People are writing spec not just with Satora.
Not about checking spec, but checking the language itself. So, for example, if you give a subset like temporal logic and an application, so how do you compare that for this particular application, temporal logic suits better than the first order logic, for example?
I do not know.
Yes, so there is no such.
I do not know.
One last question.
Thank you for Mooly for a super nice talk. So in this domain here, I mean, you kind of said why this is a killer application for formal verification. One additional point you kind of made it implicit is that in this domain, bugs do not just materialize by chance, but there's a high incentive to find them for people in order to exploit them because there's so much at stake. And now a more ethical question to you and me and all of us. How much do we help with our tools, the attackers? What is your take on that?
Yes, so that's an interesting question because one of the things that people don't like about Satora, there are probably other things, is that we are not open source. And why are we not open source? I'm sure you understand, because I do want to sell this company one day. So, but it's people are thinking that one reason to not do open source, that it's kind of a loaded gun, that basically once you release it, people can use it, and people have been trying to use Satora to attack, and we can use our tool to attack. So the answer is that, my answer is that as a technology provider, we are trying to do the best we can. I think actually if you have this technology, the bugs that people are finding in this domain, we are seeing it, it's actually, they are spending a lot of effort already in finding the bugs. We are seeing that people are really, really very good in finding the bugs. And it's very interesting somehow the ecosystem. So for example, I didn't mention in the talk, there was a bug last year which is called Nomad. You can check it out. But it's very interesting. It's again a code which was changed. And then the attacker found a bug. He was nice. He only wanted to steal a little money just to demonstrate the point. So he stole, I don't remember the exact number, but it wasn't. But then people after him, they celebrate. Over the night, they depleted about, I think, $200 million. So basically, the bugs finding, I think that actually having tools is a good thing. Having tools is a good thing as long as the tools are available to everybody and you are trying to do the most to deal with it. And we are trying to do that, and everybody. And our tool, I haven't showed the demo, but our tool is cloud-based. So in principle, we can monitor the usages. It's not, you can have a local version, it's basically implemented in Kotlin, but most of the people actually use it as a cloud-based. It's used actually a huge, powerful Amazon machines, because it's the SMT solver and the static analysis is actually and a lot of memory. So it's not so easy to use this technology. People are using this technology. In this domain, I didn't mention, but there's a lot of very, very good people, white source hacker. So there is, for example, Code Arena, there is Immunified. So a lot of people actually are good people, and they are trying to find a bug in order to prevent it, and also the bug bounties are huge. It could be up to $10 million. So we saw in the talk the 1 million, but people have got the $10 million bug bounties, and more actually. So I think tools are the answer. I think we are doing good things. We are helping the community. That's my take. And it's true that indirectly we're also helping the attacker, and we are helping the bad guys. And we should find out to say. But again, in the area of blockchain, if you didn't use Tornado Cash, you can track the attacker. So in fact, there are techniques, not by formal methods, that people track who is using it, and I think they are very useful.
Well, let's maybe take the remaining questions to the break, and let's thank Mooly again for this excellent talk.